Hi, Siddharth. Are you here? Hi, Siddharth. Do you already have your speaker here among the participants?
Yeah, waiting for the speaker to join.
Oh, okay, great.
Yeah, so sorry, I have that. Hi. Yeah, so actually, should I just join the Zoom link, or I should keep in the this term? Okay. Okay. Mm-hmm. Okay. Okay. So thanks. Yeah. Yes. Yes. Actually, I'm already in the Zoom, so I'm just asking that if I need to just quit the Gather and then into the Zoom. Okay. Okay. Thank you. Then I will just join the Zoom and quit the Gather. Okay. Thank you.
Hey, hi, Siddharth.
Hi, everyone.
Can you hear me?
Hi, Joshua.
Yeah, hi.
Hey, you're all set?
Hi. Okay, yes. Sorry, I was in the Gather and asking that if I should keep in the Gather or just join the Zoom link. Yeah.
Yeah, I mean, you can just leave it as it is and join here, and then once you're done with it, you can go back to GatherTown. Either way.
Okay, great.
Okay, Siddharth is here to help you any way that you need.
Okay, yeah. So actually, yeah, I'm okay.
Yeah, you can start.
Okay. Thank you.
Thank you.
Yeah, thanks. Yeah, thanks everyone. So it's very happy to see you in this virtual meeting. So actually, I'm Joshua. So I'm based in Shanghai. So we thought that we can have in-person meetings, but I think it's now we turn out it will be an online tutorial session. So so basically, let me share my screen first. So can you see my screen now?
Yes, we can.
Okay,
see.
great. Okay, great. Thanks. Yeah. So today, I will work with my colleague Wen, and to give you a tutorial, and mostly will be we can talk about the Vitis design storages, and also the most important will be the Vitis libraries. So we will because we can't host it in person, so unfortunately we can't arrange the labs with you because we cannot ship the board to worldwide in a very limited time. So we record a few videos about the tutorial sessions. And so in questions about why we need a Vitis platform, and what's the architecture with the Vitis platform, and what should we do, to create a custom platform or create a Vitis platform. Okay, so I will just go through this kind of topics. So so basically, I think that most of us, I think that already knows that with the AMD-Xilinx, we have the Zinc device, right? In the first generation, we call it Zinc 7000 series, and then which is in the 28 nanometers, and then we have the Zinc MP SoC platform, which is 16 nanometers. In the first generation, we have the Cortex A9 dual core, and but in the second version, we not only have the ARM processor, but also the Mali 400 graphic processor in it, and also the video codec, as you can see here. Let me find the point. Also the video codec here. Okay, so but in both generations, our design flow is typically similar to are keeping similar. So we are doing basically on the software development and then hardware development, right? In hardware, we can use in the RTL or using the using the Vivado HS, right, to generate the hardware history. And then, or we can use the MATLAB or other hardware development tools to develop the hardware. And also, we'll have the software development kit, SDK, to build up the software platforms, software designs. Right? Then it will combine into an embedded system, which has the L file for the processor and the bit stream for the programmable logic, right? So it turns out, if we go to more details, it will be very traditional way. We use the Vivado to generate all the hardware part, during the IP part, and then we use a SDK ID to create the software part and combine them together and download to the board, right? So now today we will introduce a new flow. We call it the Vitis platform flow. So the Vitis why we have a Vitis platform flow is that because basically in the latest two tools, we are trying to unify all the tools in software development into one unified environments. We call it Vitis. So we will keep the hardware parts as Vivado only. Vivado design suite will only for the RTL design, traditional FPGA design development, and then for all the other softwares, including the OS firmware, the previously we called SDSOC for the embedded side, SDXL for the data center side, and the AI inference. All of them are all together as a unified platform. We call the Vitis Unified Software Platform. Okay, so this is the basic background of the Vivado and the Vitis and how we position Vitis. And why we do it? I think one of the reasons that our technology is ramping up or evolution very quickly. And if you look at our latest platform, we call it the Versal ACAP. With the Versal ACAP, we not only have the the processor, the programmable logic, but we also have the AI engine, right? So AI engine is a kind of is on the top level. Here is top level hierarchy of the AI engine architecture. It actually it integrates the two demonstration 2D, the 2D areas of the AI engine area here, and each AI engine actually has integrates a very long, instruction word processor and integrate its own memory, and also interconnections for the streaming configuration and also the debugging tools. So if you look at this very heterogeneous and complex architecture, to be honest, if you're using the traditional Vivado design flow and program each small elements, I think it's a huge development workload for everyone, for every engineer, And if you do all the things are very, very micro programmable, it will take a very long time to develop such super heterogeneous system, right? So that's why I think we want to have a platform-based design flow. Now we call it as a Vitis platform-based. So our idea that with the Vitis platform, we can enable all the developers, from different levels, can develop within Xilinx, AMD-Xilinx environments. As we mentioned, for the hardware development, we can keeping using Vivado. It's well for customized RTL development, right? And then for the software developer, they can still using Vitis to design and reuse some of the accelerator applications. And then with embedded developers, actually they can with the Vitis platform, they can develop all the embedded and even to the kernel side and the file system side. And with software with the AI developer, they can use our Vitis AI tools to develop all the AI applications. Okay, so with Vitis tools now, so you can understand the background of Vitis, right? So then basically, so we know that FPGA is good at the application acceleration, right? Traditionally, FPGA development requires the hardware knowledge of the RTL design, right? But nowadays, FPGA is used more and more widely, and we wish to enable all the developers to build application upon FPGA, and not only FPGA, actually but also on the SoC, on the AIE platform, and also on the Versal ACAP platform. And it's besides that, it is very common that several products in one product line has a similar functions, but different form factors, right? It would be best if a developer an application could be deployed in different, in different regions, or different platform, so that we can reuse the algorithm and implement at the maximum level, right? I think this is also the idea. Not only it's not very new. It came from the Vivado. Also, in that time we call Vivado one of the key component of Vivado that IP reuse, right? So we want to have the users to reuse their components, their accelerator algorithms, right? So now I think that with the Vitis platform, we are trying to target all of them into a unified platform. So this is another background of the Vitis. So how our Vitis platform achieves this? So basically, this is a high-level diagram of the Vitis. So it defines a hierarchical software platform to enable all developers. Actually, Vitis provided their accelerator IPs here. IPs, or now we call it libraries, right? Open source libraries and the domain-specific development environments, such as for the AI part, we all have the domain-specific supporting the Vitis AI, supported TensorFlow, PyTorch, Cafe, all the frameworks, and also we all have the video libraries, which is supported, for example, the FM pack for video. And the application developers can work in this environments and think less about the low-level implementations. Those deployment implementations will be defined by a series of acceleration operations will run on the acceleration part automatically. So Vitis allows the users to develop the acceleration kernels with RTL or with the C language. So the hardware engineer who knows about the RTL and the software developers who knows about the C or C++ can both work with their preferred languages. Okay. So to enhance this kind of reusable and portable of the applications, so a software layer, we call it the Xilinx runtime library, or XRT, and a layer of the Vitis target platform connect between the user programming interface and the deployment targets. Okay, so the XRT provides a unified software interface for the high-level applications, so that the control of the high-level application is transparent to the hardware. The platform can translate the commands into different deployment targets according to the hardware features. For example, the DDR controller implemented by our MIG IP and by the MP-SOC PS DDRs has the same hardware interface. Acceleration applications can adapt to these two different platforms with no code modification. The embedded platform and the data center platform, the embedded platform and the data center platform have a unified architecture. So one application for example, if you design an application on embedded side first, on embedded platform, but you found that you need more, computing resources or more powerful processors, then you can move to cloud-based, right? So, or you first develop an application based on the cloud first, but you found actually you don't need use that much resources. You can move to edge side. So by the time with the Vitis platform, actually it will be very easy for you to port from the cloud to edge, or from edge to the cloud. So this is another benefit, because as we mentioned, the hardware part will be, the interface part will be transparent to the application level, right? So this is a major advantage of the Vitis. So because we have as we said, we have the runtime, or we call it middleware for the whole application development. So this will be next page will be more clear to you. So with the Vitis platform, we have this kind of XRT and also the target platform, which resolve all the interface and the drivers for you. So users can can only need to target the dynamic or your own acceleration parts. So and also in the XRT or in the target platform, we provide this kind of what tools we call it the analyzer, especially analyze and debug inside it. So this is we call it the Vitis platform. And here is actually the example with the platform. So for the Ivory class, we have the PCIe interface IP core and the DMA in the platform, in the target platform. And the acceleration kernels can be switched from different applications. In one case, the kernel can be the gzip algorithm accelerator. In another case, the kernel can run the acceleration we call it acceleration algorithm acceleration. So the platform can serve these two kernels well because the kernels only requires the fundamental platform features like the PCIe channels for data transfer and the local DDR memory access for the data storage. So platform can support different applications, and the acceleration kernels can be applied to the different platform like the U200, U250 with no code changes, and it can also move to the embedded platform. For example, this U112 based platform, which works very well. So I think this is a kind of example of it. And there's another example for the customized embedded platform. So suppose you have a board with a MIPI interface for your camera input. And in that case, you can provide a platform with the MIPI video IP, and the application developers can use it for different application. For example, it can work with the video encoding. It can also work for the video analyze, and the analyze can be target for the analyze can be different based on the algorithm. It can be the objective detection actually, or it can also be the other applications, for example, the object recognitions and with or without the machine learnings. But with the hardware side or interface side, you don't need to change it. Okay, so similar actually, the application can easily port the developer can easily port the applications and the acceleration kernels to other platform with the same interface. For example, when the board updates the DDR capacity or shrink the form factor, it only needs to rerun the implementation after updating the platform. So the application code doesn't need to change it. So my personal feeling is that it's more like a software, right? A software library help you. We make the hardware development or application development more like a software development. Okay. So with this, so for the example above, so you may have some draft ideas about for the customer platform or how we create a custom platform. So in general, the platform provides facilities to kernels in a standard AXI interface, except general facilities like the clock, reset, and the interrupt signals. They mostly translate external IOC interface, especially the data channels, to memory map AXI interface or AXI stream interface. So if the IO interface should be controlled by the processor, it doesn't need to export to the kernels. Okay, so for the traditional FPGA development flow, we understand that it's quite flexible. User can do anything with RTL, right? So flexibility is a double, but flexibility is a double-edged sword. It reduces reusable and leads to a longer development phase. So the Vitis platform-based design methodologies helps on the flexibility in some ways, because the application developer can only use AXI interface, but improves the ease of use, right? So we have the standard, interface. Now is AXI. So this change will actually bring the benefits to the ecosystem or to the more widely developer community, right? So with the traditional workflow, it's a common problem that the components are not in a standard interface, right? So that's why we need a high level architecture using XI. And besides that, all the tests, for this IP are usually on a specific context. So when the context changes, it's need additional efforts to verify and fix the bugs. So to make this kind of component more reusable, we have this kind of standard interface. And once we standard interface, then it will be easy for us to have the ecosystem involved naturally. So, and also we have this kind of, applications. This will be accelerated from the, from the hardware side, because the interface will be the same, right? And the drivers will be same. So we can not only reuse IP, but also reuse the software part, reuse the hardware parts. Okay, so that's why. So we said that the Vitis design is kind of requires a platform and the application. So the Vitis platform handles all the hardware and the software side, and there are two basic types of the platform. We call it the data center platform and the embedded platform. Okay, and the data center platform works as an accelerator for the x86 CPU host. And the CPU host will talks to the data center platform through the PCI interface. Typically, our other platform like U200 or U200 250 are these types. So when the data center platform includes an ARM processor, the developer can use this processor. It is called a data center hybrid platform. Currently, this kind of platform is not public yet. So, but on embedded side, I think that most of us are more familiar with. So the embedded side actually can work by themselves. They don't need the external host. We already have the processor inside of the embedded platform. So when the design needs the acceleration kernels on the PL or on our future AI engine, the platform needs to be an embedded acceleration platform or the extendable embedded platform. So when the PS and the PL are designed separately by the hardware and the software engineer, embedded software development platform would be good. It doesn't support the acceleration kernel on the PL or engine, but only works for the software development. The platform creation, it will be more easy or more simple than the Vitis platform. So this is we call the traditional Viado and SDK platform. But nowadays we are talking about the more embedded acceleration. So since the embedded course you will be more focused on embedded acceleration, then we need the embedded acceleration platform, and this is the most important part of the current Vitis platform. So in Vitis platform, we call it as a platform-based acceleration application development. So in all the acceleration use cases, platform provides a hardware interface to the application developers. It includes the various hardware interface into logical interface. Platform also provides various functions to application developers. For example, they would provide at least one memory controller. Sometimes a platform can also provide the board management features and the security features. On the software side, embedded platform provides a complete set of the operation system and the runtime library so that the system can boot properly and the acceleration application can use the platform hardware functions. So this is on the software side. So the whole application developers can only need to then focus on the creating the host application and the acceleration. So the host applications, right, and the kernels, because as we see that Vitis Tactile platform, we resolve makes this part transparent to the application developers. And then, so if we match this kind of concept to the files, the hard platform is a special Viado design with all the IP functions and the special metadata properties. The hardware platform is archived as a XSA files. Okay. We call the Xilinx, if I remember, Xilinx system ACAP, right? So it's different than previously file name, right? Previously, I think, if I remember correctly, we called it HDF file. Now we call it XSA because it contains more data to let the software environments understand what hardware it is, you know. And the software platform should contain one Linux domain. Actually, the Linux domain should be, you know, not only define the Linux components such as the kernel image, root file system, device tree, but also how this Linux can boot properly. So the BI file for boot image description care and all components required by BI file, BIF, such as FSBL, PMU file, firmware, U-boot, device tree are all needed. And the system root is usually, you know, provided for host, you know, application cross-compiling. It provides the libraries for the host application. So based on this platform, user can grab extraction kernels and link them with the platform hardware and generate one, you know, XCL bin file. So cross-compile host application with the system root to Linux ELF, and the package the ELF file with the Linux images and the boot components into the final SD card image. So after the Linux boots up, the user can execute the host application to load the XCL bin and run the extraction algorithm. So this is the way how we build up a software extraction kernel upon the Vitis platform. So there are two ways to organize the software components. First one is we package them into the platform. That means all the kernel, root FS, and the system root are usually very large in space. They can take the you know tens or hundreds of megabytes. When we create a platform, we can package them all the components into a platform, or we can defer it to the application creation time later. So Vitis allows the user to use external software components because it makes the design more flexible. When the software components need an update, then we should leave the, you know, software component outside the platform package, and we can skip it again, skip it, and then we can package them later. At the same time, it also allows the multiple platform to share a set of software components. So later we will show a demo that we download the COM image, you know, from the Xilinx website. It includes this kind of root FS or kernel or root system root, and then we can assign with the system project and build it Vitis platform. Okay. So above we talk about some you know, concept of Vitis platform and the benefits of it. So usually we have got a question. So well, Vitis platform or Vitis makes designs more complex, and it's a frequent asked questions, right? So our answer, I think it's not very easy to answer, or it's the answer is a yes and a no actually. And Vitis can make the designs simplified with a pre-built platform. This is our answer. Okay. So it will indeed take more time if you every design start with a creating a platform. Okay. But in most of cases, a design can start from a Xilinx, you know, pre-built platforms, because we think that the designs will be, we can start with a Vitis platform. The design development process can usually divide into several steps. The first, we evaluated the key features, right? In the evaluation phase, we evaluate to the key features that our design intends to use. If a Vitis library provides this kind of feature, we can access it on the base platform. If we need to build any customer kernels, we can link them to the pre-built base platform. Okay. Only when the platform needs more advanced interface, we can customize the platform. Okay. So then it will be a customized platform. Okay. If the evaluation shows that functions and the platform of these key features can meet our expectation, we can migrate the evaluation platform to the final production hardware. Otherwise, we can stop early and find other solutions. So in a traditional flow, you need to spend some time set up in evaluation environment first. For example, the camera interface, right, or the PCI interface. So with Vitis, it gives you a shortcut to the evaluation, the key features first on the Xilinx demo board or with the Vitis emulation when the hardware is not available. Okay, I think the Vitis emulation is also very key features in the Vitis toolset. So we will start with a pre-built platform, as I mentioned. So we on our Xilinx website, you can very easily to access it. Xilinx.com and download. You can find the host the Vado tools or Vitis tools, and also there's a Vitis embedded platform, right? So we hosted this kind of pre-built base platform on the download center. First, you need to download the platform to your development server. Then you can go to the Vitis embedded platform tab. You will see the base platform here, right, on the different boards and architectures. And if the platform called a base platform, it is a static platform. For a static platform, the hardware links results contain the 4-bit string, a 4-bit configuration. During the system boot, this bit is loaded when the host application executes the XL bin file. It only reads the metadata from the XL bin. Another type, it's called the DFX platform, can dynamically load the kernel PL configuration during runtime. When the system boots, the only platform hardware is loaded. When the host application downloads the XL bin file, it runs the partial reconfiguration for the kernel hardware and reads the metadata from the XL bin. So most of the embedded execution design or evaluation part in the evaluation phase, we can use the static platform. And if you remember, in 2 or 3 slides before, we mentioned we deliver the software components, right, separated from pre-built platform. This we call it the common image. Actually, as I mentioned, it includes the kernels, rootfs, and the system root, and also the boot components. So we can use it to build up the platform for your own custom boards. Okay, so this is 2 types of download files from the from our website. So to install this kind of platform, you just need to extract the package into a Vitis recognizable path. Vitis can recognize platforms in 3 platform search paths here. Okay, you can set up the platform in either path. Just extract your downloaded package into it, and you can extract software component to any path actually, and provide the path to Vitis when you creating the platform. Okay. So to use the platform, so when you create an application in the Vitis ID can list the platform in the search paths. So you can all the platform you have extra or download, and then our tools will detect it and list it. And it also allows you to add more platform when creating the application. Okay, you can still add a platform during a GUI. So when you select the domains, it will ask you for the software components locations. So if you are using a command line model, you can pass the platform name and the system root to the V+ package operations. Okay, you can use the command line also. So this platform usage flow is the same for the pre-built platform and the customized platform. So it will be all the same. Okay, and you can also install additional software with the package fees. Okay, so the target for the Xilinx pre-built based platform is to provide the extended features, but leave the maximum programmability to Vitis users. So to make the software easy to use and extendable, we provide a package feed, or we provide a package feed, so that the users can install additional software package on the file. So that's even if the root file system in a common image doesn't provide your required software, right? For example, in maybe you are familiar with the ping, right? In the ping, the Jupyter, the other software Python package doesn't include in the Xilinx common image, but we can still add it, right? And we can install them with the DNF, package manager, okay. And the Attendees package fees provides all the software packages supported by the Attendees, okay. So you can find more information on our user guide, UG 1393 for all the detailed steps. Okay, you can find this user guide about the more details of using the Vitis platform. Okay, so so now we covered all the basic idea of the Vitis platform. Before I go to the create custom platform, I like to show a demo video to you first. Let me see. 1 minute. I'm opening the video. Okay, so we just record a short video about creating a Vitis platform. Okay, so basically we download as you can see, we download all the platform into a specific into our own PC, right? And then extract to the folder, and then we installed it in the Vitis platform path, and then we launch the Vitis IDE. Now we are launches the Vitis IDE. And then this is the common image we just downloaded from the Vitis platform. Okay, and then after we extract it, and then we create the Vitis platform here. Because the common image we downloaded doesn't include the FSPL, and we are using the common image and creating the FSPL file for our platform, for our board. We are running because FSPL is running in a standalone model, so we select the operation system as a standalone here. This is only for the FSPL. Okay, and after that we can just use this Vitis IDE to create the FSPL, right? Okay, so because of time limit, I will move much more quickly. Let me find the path of the. Okay, here we already built up the FSPL here, and now we have the Vitis platform here, right? Select the XSA file, right? And then because we already created boot commands in the previous steps, now we can just build the application upon the Vitis platform. And we needed to select the FSPL and the PMU management firmware for the for our platform. And we select all the SD card folders to all the files who generate all the boot components here. Now we select all the files needed for the platform. And now after select all these files, then we can go to build the platform. Okay. Then after we build the platform, then we can add the application upon it. So let me go here. So now we already create all the platform, create a platform based on the Vitis, and the platform can be used for all the other applications. Okay. So we are using one application, very simple application called VADD, or VADD to show how we create acceleration kernel for it. So this makes this makes acceleration design flow as simple as a software. So if you have experience with our previous design flow, right, in the Zinc SDK, with this kind of Icarus based SDK, you can build the software application upon it, right? But now with the Vitis platform or Vitis acceleration flow, you can build up this kind of acceleration just like a software. I mean, because in the Vitis platform, we handle all the interface or handle all the drivers behind. So now we using Vitis HS to create the VADD accelerator in this SDK, and after we generate the hardware, generate the platform new platform files, and also generate the kernels, hardware kernels, it will automatically connect and also build up the drivers for all the acceleration if necessary. Okay. So this is some of the basic idea of the Vitis platform, and we just need to find download the common image, right, from the Xilinx website, or if you already have the board like the 102 board, 104 board, or KV260 board, which has a pre-built platform, you can just download the pre-built platform and open it in the Vitis IDE and build your acceleration kernels here. So it's quite simple, to be honest. Okay. So then we can go to the how we create own customer platform. Okay. So if you have a custom board, and how we create a custom platform. So we call it the create embedded acceleration platform from scratch. Okay. So in this of the design flow, so in the high level workflow, it will be we need a base bootable design, and then we need to update the hardware, update the software, and generate the platform, and then we need to do the platform verification. Okay, it's the high level of the what we needed to do. Okay, and the first thing definitely is create the base boot file. It's mainly, as you can see, we created the actually in the previous video we already show you we create this FSPL, right? And most of the components can be provided by this based bootable designs. And then when we created the platform, the tasks are mailing, updating the components for the Vitis required based on the Vitis requirements. Okay. And finally, we validate the platform before delivering to the application developers. Okay. So this is the flow. So a base bootable design with Vivado, we designed it with Vivado and the Parallelism image that can boot the hardware to Linux OS and give the platform creation a good start. Okay, so basically it will need to resolve the Linux boot up and the Linux OS. And a board bringing up is a time-consuming job actually. So for the new hardware design, right? So that's why it need to be done no matter with or without Vitis design flow. So everyone needed to do it. And but in the Vitis, and we should it's important to make sure your based based bootable design is correct before going forward, because it gives you the clues to accelerate the root cause if the generator platform encounter any issues. So I think this will be more important. And the preface on hardware should be tested by this based bootable design, because when you deliver a Vitis platform to an application developer, most of them maybe have no experience on the low-level hardware or on the bootable designs, right? It will be difficult for them to debug this kind of root cause. And once the base design can be booted properly, and then we can start to update the hardware for the platform based on the platform requirements. To make the hardware design compile with Vitis platform requirements, we need to check whether it can provide those signals like the clock, the resets, or the clocks. And one clock is and its associated reset signals memory, and one clock can be can be the default clock. You can add more clock reset pairs for better flexibilities. So you can have the PR reset, PS reset, and other resets, right, based on your design requirements. And then the XI interface can provide the control channels and the data channel between kernels and platform resources. Usually we'll provide an XI master to control kernel start and stop. And the kernels need to access memories, memory controllers in the embedded platform also. So this is we have the XI for memory, right? So the platform needed to explore the XI slave interface so that kernel can use the memory. Okay, and another thing that the XI stream, and especially XI stream is especially good for the streaming data like the audio, video, and the ADDA. It's done to have the address information like the memory map XI, but normally it will be very useful for this kind of for example video, as we mentioned, video streaming data processing, right? And then we need to consider about the interrupt. So if interrupt is not available, our XRT runtime will run in a pooling mode. In general, interrupt is recommended because the interrupt model would allow the processor to work on other tasks instead of checking the kernel status regularly. I think this is what we come on edit. Then we can export to the XRT. So when you build up Vivado projects in hardware side, the hardware update will be done actually in the Vivado. Before you do any steps, any setups, so make sure to set your project as an extensible Vitis platform. If it is not created in this way, you can update it in the project setting. Okay, again, in the project settings, you can again select it as an extendable Vitis platform. So I think that if you are using, for example, Vivado 2018 or before, there's no such options for you, right? After that, I think since 2019, there have been a new tab allowed to
select. Actually, this is for the to create the Vivado project as an extendable Wattis platform, because if you select it, our tools will know to add some of the Wattis platform hardware components to your Vivado projects. Okay. And then in the platform setting in the Vivado GUIs, you can select select a platform setup. Then you can enable the XI, the clock, and then interrupt the sources. Okay. And then in the Vivado, in the block diagram, actually it is almost the same. I think. Actually, in the hardware design flow, I think who has the experience with the Zinc development in Vivado, actually the flow is almost the same, except that you need to select the option to create as an extensible Wattis platform. This is the most key option that you select, or different than previously. Okay, and then as the rest actually will be all the same. And then the Wattis will, after you generate this kind of kernels, then Wattis will connect the kernels to the available clocks and reset and excite and interrupts during the link stages. Okay, so this will be done actually by the Wattis platform. The users will not do it. So okay. And another example will be on the Versal. So in the Versal design, more advanced design, actually the requirements will be similar. The new blocks like the XN knock, right? XN knock and the X engine makes the block design looks more complex, but the rules are the same, because we still need the clock, need the reset, and then need the XI interface, and need the interrupt. So these are the different types. So the only thing that there will be some new components between the latest Versal platform and the previous Zinc platform. The others will actually will be almost the same. And then we can, after the hardware setup, and then we can export the XSA. Okay, we can create in the Wattis ID GUI, we can select the file, export the platform to the XSA for software design. Okay. Then in the Wattis software design components, then we need the updated softwares. Okay, the updated softwares means Linux actually is required, because the acceleration kernel needs to be controlled by the XRT. Okay, and the XRT currently only supports the Linux on the ARM. Okay, if we already have a working Linux environments from the base bootable design, we need to update the software environments to enable the XRT. Okay, we need to enable XRT. The XRT package and its dependency, including the LCL drivers, link drivers, and need to be installed in the root file system. If you need a native host application compilation on the ARM, could you also install the XRT development package? Okay, this kind of packages. And there are no special requirement for the Linux kernels, because the kernels already boot up. During the boot up, kernel will be the same as the previously. Okay. So it looks at the requirements, it's complex, but actually since Linux, we have the Linux, right? Does a good job of the authentication. The actual user manual work is actually the minimal. Okay, and then we can see. Then after that, we'll see the we have the Linux, right? And through the Linux config for your rootfs, you can actually add the XRT packages. So the common image we mentioned for the pre-built platform can be used for custom platform as well. Okay. The device tree generator can generate XRT required nodes if it's a XSA file,
the hardware export XSA files and extendable platform projects. And the Attendees actually detects the XSA types automatically. So it will, because in current Vivado, after you select it as a extensible Wattis platform, our Attendees will detect it and understand how to configure the Attendees for what is platform-based design in the software side. Okay. And then you can simply generate the Wattis platform. Okay. After we created the hardware XSA and the software components, now we can link them together and create the Wattis platform. So since the BI file and the boot component directory path will be provided to the Wattis generated platform, we usually copy all the boot read files into one boot directory. Your boot generated by the Attendees will need to be placed into the FAT partition on the SD card, so we can copy to another directory. Linux component are optional to platform because they can be added during system project creation. Okay, so in the Wattis 2021, we can generate the default BIF file. You only need to customize the BIF file when there are more requirements of the boot flow. Okay. And we can create the Wattis platform in Wattis IDE by creating a new platform projects. Okay. So as you can see, it's quite flexible. We provided the hardware XSA, we provided the XSA file, hardware XSA file, and create a Linux domain. Okay, set up the required field of the Linux domains, generate the platform by clicking the build icon. Okay, this is what we showed in the previous video, and the general platform is in the explore directory. So we can actually definitely use the command line to create it. Okay. And then next, the final step actually the verify platform. Okay. So the platform creator should verify the platform before delivering to the application developers. So we can check the platform metadata with the platform information utility. So if the platform has a memory map XI interface, we can use a simple kernel such as we just showed the virtual add addition, VADD. Features such as the clock, the XI for control, XI for memory map, and the interrupts. If a platform has other special interface, the platform developer should prepare for other test cases. Okay. So platform developer can also enable emulation for platform and running emulation before delivering the platform. And so this will be a more advanced features. It will not be covered in today's today's session. Okay. So in a short summary, so I like to see the platform creation process has been simplified in the 2021. We have several either use environments enhancements. Okay, so basically I like to say if you already have the board that has already had the pre-built how to say pre-built platforms, you can just download the pre-built platform and launch the Vitis IDE and select the platform and build your acceleration kernels upon it. Okay, and if your board doesn't have the pre-built platform, you can download the common image and build up the platform based on the guide that we here, right? We should build up the base bootable design and update the hardware, update software, and create a platform. And after that, actually, you can use the platform in whatever your application. Okay, this is about the Vitis design flow. Okay, so another thing that I want to, we already showed demos before. So I like to recommend that we have several, very useful reference. Okay, and you can not only look at the Vitis user guide, and you can also look at the software platform user guide. It is UG 1460, and we also have a GitHub. Actually, our GitHub I think provides the latest materials and the tutorials steps. Okay, so actually I think I will recommend this as well. So you can go to github.xilinx github.com and then /Xilinx and then search as Vitis Vitis tutorials, and you can find the Vitis platform creation and how to use the Vitis platform. Okay, so this will be very useful to you. Okay, and actually another very useful thing that our Vitis also provide more than 500 functions across multiple libraries, especially I think on the vision, on DSP and the fintech and other basic math libraries. So this kind of library can help you to accelerate your kernel acceleration kernels. I think this is also very useful. Okay, so my colleague Wen will give you a talk about the Vitis library just after me. Okay, so this is all my parts. Give you a brief introduction of the Vitis platform and how you create the Vitis platform. You create your own Vitis platform. Okay, please feel free to let me know if you have any questions. If you have no experience with Zinc, maybe there are too many new names. But if you have any questions about the names or flows, please feel free to let me know, either on the chat window or on Q&A or just talk. Okay. Okay, so if there are no questions currently, I can invite Wen, my colleague Wen, to give the next talk about the Vitis library. Hi,
Okay,
Wen.
here. Hi. Do we need a break for 10 minutes, or I just started right now?
I think because it's online, we can just go. Everyone who need a break, yeah, take a short break. Yeah.
Okay, I will share the screen. Here's my screen.
Yes.
Okay, thank you. Greetings everyone from all around the world. I'm Wen Chen from Xilinx, from AMD-Xilinx University Program Team, and I want to send our warm welcome to you for our topic on the Vitis Vision Library. So let's go ahead and take a look at what we'll be covering today. Since there has been a previous training on Vitis and the knowledge of Vitis is prerequisite for this course, we won't be spending a lot of time talking about the tool flow outside of how Vitis design methodology applied to the Vitis Vision Library. If you leave this section feeling like you need more information on Vitis, we have more Vitis training video and user guides on the official website that I highly recommend it. We're gonna spend about 10 minutes looking at the whole Vitis accelerated library, just orient ourselves before we do a deep dive into the Vitis Vision library. We will take a look at the GitHub repository structure and how you can expect to navigate the further hierarchy in there. We also briefly have a snack preview regarding the programmable logic and AI engine design flows that are used with Vitis Vision library. Finally, wrap up our section with some Q&A time, so we can answer some questions. And before we get started on the introduction on Vitis accelerated libraries, we have prepared a customer role on which language do you prefer for development. So here is the result. And the result of the customer poll revealed something about the majority of the designers out there thinking using FPGAs as their adaptive computing platform. So I told us, so those designers want to develop the off-the-shelf libraries and frameworks whenever possible. So they don't have to reinvent the wheel and maintain their own agent library of IPs. And it also told us the application developers trained to do the majority of their work using C and C++ and Python. So when the Vitis architects designed this tool flow, they use the worldview as one of their primary motivations for enabling designers and developers of new products to maximize their productivity. One thing I will note here, if you haven't already, is the third largest segment that comes into play for language is the Python. So it is kind of reflects a little bit on our book. It is definitely growing popularity for embedded users. So some of the same lines, Vitis architecture realized that more advanced libraries would be consumed by designers looking to squeeze the maximum performance out of their adaptive computing device. So they thought to build a vast library of those commonly used HRS functions, which would later evolve into Vitis accelerated libraries. The Vitis HRS tool is a high-level synthesis tool that allows C++ and OpenCL functions to become hardware onto the device logic fabric and the RAM and the DSP blocks. If we have today for math, statistics, linear algebra, and DSP offerings, this gives us a set core hardware accelerated functionality for a wide range of diverse applications. And these domain-specific Vitis accelerated libraries offer the designers out-of-the-box acceleration. This is needed for workloads like vision and image processing, quantitative foundation, and data analysis. Data compression and its list is continuing to expand in every new release. Yes. Today, we are really going to be spending the majority of our time focused on the Vitis Vision library in order for any of these by the Vitis accelerated libraries to be useful for developer wishing a program with them. We need to work with the commonly used program language like C, C++, and Python. And the libraries could be linked in the applications at runtime to play CPU-only library calls with ones that leverage Xilinx and device acceleration. Also, since application developers would not have to understand the RTL design, this would enable them to develop their own accelerated applications much more rapidly than traditional FPGA designers. Finally, Vitis developers will not be forced in using or learning a new framework or language, or writing programs that execute across heterogeneous platforms such as OpenCL. And so since the accelerated libraries are accessible to GitHub and they are scalable across Xilinx platforms, this enables developers to take a write once, run on many hardware platform approach if needed. Here we see a developer writing an application which uses the Monte Carlo simulation to model the probability of different outcomes in a process that can't easily predicted due to the intervention of a number of random variables. The result is that they are then able to estimate the expected payoff of European option type, which allows for early access of options in this fintech application. So these solutions are scalable, and these accelerated applications can be deployed at the edge, on-premise or in the cloud without having to re-implement the adaptive computer accelerators better leveraged by the application. So all Vitis accelerated libraries are licensed under Apache 2.0 license, which is quite permissive. And then the users won't need to pay AMD-Xilinx for the code, and they can charge their customers for products but built by the accelerated libraries without having to pay any royalties. I can modify the library code or give it to anyone without having to tell Xilinx or obtain permissions to do so. Since the only legal process for licensing this code under Apache 2.0 is already done on the Xilinx side. When we perform a legal sweep of the code prior to the release, in order to verify that we are not releasing any property of information or intellectual property about our device that we are not willing to reveal publicly. This huge advantage for the software developers can design their own hardware accelerated platform using this library, and they don't need to follow the traditional FPGA development path in order to do so. Finally, if custom accelerated kernels are needed, then we will see how lower level library functions can be combined and then tied into their own application, which enable us to target our adaptive compute hardware. So understand what we mean about higher level and lower level functions. Let's break this down a little bit to understand how this works. So imagine that there is an office building here, and which represents the 4 hardware and software solutions made to our product. Level 1 and level 2 functions here, down here is at the bottom. These ones represent the substruct level support areas of the office building. This is where to the boiler room, the mail room, and the data center reside these areas. These optimized functions are used to build kernels, and the library kernels reside right on top of the FPGA fabric and the AI engine hardware. Just above those layers and under the level 3 layer, you will find the Xilinx runtime level. And this is where the folks can enter and lobby the building. People can have a general understanding of what is underlying support infrastructure underneath them on the basement floors. The office worker, they likely gonna to speed up to the upper level 3 and higher to the office above, which are represented by the apps. And the level 3 API is appear. And here, the high level applications are assembled. In order to make use of the API abstraction that enabled by the operation of the lower layers. Here is there is really an oversimplification that we given on how Vitis library in structure. But by arrange our Vitis library in this fashion, enable the developers to interact with those library and all the 3 levels. And there are many example applications that are provided for the virus libraries, showcasing means level 1, level 2, and level 3 capabilities. And the developers can also modify the primitives as needed to fit a particular application, or they can use them as templates for creating new primitives for their own accelerator library without any licensing restrictions around this, or having contributor changes back to our repository. And from a higher level perspective, these new custom kernels can be created by combining existing and the custom primitives along with kernels to create new libraries. And the developers can also modify this library API as needed to support new functions and the system configurations. Here we have our GitHub repository for all Vitis accelerated libraries. This structure hierarchy is relatively simple for each of our accelerated libraries, such as math, statistics, linear algebra, DSP, and vision. You will find everything that's needed for developers to get started, including the documentation in the primitive kernel, the software API source file folders. For each of the level 1, level 2, and level 3 source code folders, we also provided tests that can be leveraged at each level, along with example usage for the level elements and some information, which can be used to compare to the CPU-only implementation of those computation blocks. So let's take a look in these design flows that can be used with Vitis accelerated libraries. For an application is ready running entirely either on the x86 or on the embedded target. If high-level API could be batched to the level 3 functions already built up for an accelerated library, then XRP can simplify the code to reach into the accelerated design kernel running within the shell of the target hardware down there. The custom kernels are needed, and the level 1 and level 2 functions can be tied into the Vitis application and targeted to the adaptive computer hardware using XCR bin with the platform that is built by the Vitis tool. And library kernels and primitives can be compiled stand-alone accelerator or combined with other Vitis accelerated library like math, statistics, and even partners libraries to accelerate custom and processing pipeline. In fact, there is several accelerated libraries that have level 3 Python buildings and level 3 Python bindings using C types to wrap the level 3 API in pure Python. For those Python functions, we need to build a shared object library or .xo file using makefile in the level 3 software, Python API locally. And this makes 3 functions easily callable from Python applications, which is another language that we saw is growing in popularity among the customers. So now we have a higher level of Vitis accelerated libraries. Let's dive into one of our most powerful and isolate libraries that we have available, the Vitis Vision library. So to give you a little bit idea on the story of Vitis Vision library, keep in mind that our original inspiration was OpenCV. And we are gonna take a look at some of the ways that it is similar and some of the key difference between OpenCV and Vitis Vision library. We also explore some of the key highlights. First being that was intensive functional and hardware coverage. These cover a very large breadth of function and can be deployed to many domains due to the good application coverage. As easy to use, offering plug-in and play capability. It is also open source with Apache 2.0 license, and it is a framework to support common infrastructure for computer vision applications, just like OpenCV inspiration. Finally, since we are using the adaptive computing device, whether it is based on our Link embedded device or Versal hardware or Versal ACAP hardware, we have a lot of flexibility for performance with this device utilization that we can trade off within a design. For programmable logic designs, we can vary this MPC number here. The MPC number is not a video game character, it is the number of pixels for clock measurement that we are used to increase to 3 points at the cost of additional hardware resource. Likewise, we can deploy peeling across multiple AI engine cores to achieve better performance on and higher resolution, such as 4K and 8K video streams. And lastly, we now have several Vitis Vision-based pre-processing pipelines that are available. As example, you can think of this as fully customized image and the signal processing and signal processor ISP. Where OpenCV is being around for a very long time and has become the world's most widely used computer vision library. This year, they are reporting some 18 million downloads. Since it is considered in the golden standard for Vitis, golden standard for computer vision algorithm specification and countless designs that are used to baseline their software implementation for their own design. It is originally started as a C++ project for all those years ago, and evolved to also offer Python wrappers. It isn't just a demo platform or academic exploration in the computer vision. There are very many real-world and real-time applications that are deployed on the world today, which uses OpenCV in some way. It is important to understand that it was initially an inter research initiative that was officially launched in 1999 to advance their CPU-intensive applications, and it was part of a serial project including real-time retracing and 3D display worlds. So we see that OpenCV is our inspiration for Vitis Vision Library, and we will look to see how having a similar API signature enables easy plug-and-play replacement of CPU-only functions with the Vitis Vision Library equivalents. So what are you gonna run into? It is different by Vitis Vision Library when compared to OpenCV. There are 3 key differences we're gonna explore here. One is the result of computing of the computer vision output using a fixed point rather than the floating point implemented you might find on a PC. And the other difference here is that we look at our stream capability and why that's a big stream capability and why that's a big advantage for us. And finally, we are gonna take a look at the idea of parallelism. And since that is another huge advantage for us over most other solutions. So here you can see how the OpenCV API signature served as inspiration for the hardware accelerated Vitis Vision Library. If you look closely, both of them have a pointer to the source array of data, and it is image data. Here you can see also have a source pointer down here, and both are the pointer to the output. Both are the pointer to the output and or the destination array of the image data. And this is where the result of the function will get stored into. So here we also have a destination, and there is also some types that get passed along the settings, allow for the settings of options such as resize, interpolation, computational method. Here we are using this interlinear method or the type of resize interpolation. That is being implemented. So very familiar API functions cause those two. And there are some additional differences to be aware of hardware accelerated by vision libraries. And the big ones to be aware of is the fixed point computation. There is a lot of information on the slide that you can help to explain more things in short, because the fixed point rotation has a binary point between the integer and the fractional bits of some operations. They would normally use floating point operations. This ends up resulting a small error being introduced. We compensate for this. The fractional bits represented are chosen in such a manner that that any error introduced is minimized in comparison to the floating point vision of some operation. And the good news is that the technique results in a computation error that at a maximum 1 bit. That is the least significant bit per cycle. That is the least significant bit per pixel value. For imaging, the difference is so very slight that it is rarely noticeable with our naked eye. Here we can see an example of this with a computational example of our favorite resize function that we just looked at the API before. Then this is being leveraged once again to move an image down in size from 1080p solution source image down to a 720p resolution output image here. And you can see there is an imperceptible difference between the OpenCV output and the CPU-only implementation. On the left, it is a full floating point computation. This is the Vitis vision library output using the fixed point computation, as being shown on the right. Another difference for us from OpenCV is the streaming support, which gives us the ability to transmit or receive continuous data over a network or interface in a steady flow. This is important because there are many applications that exist in the real world which need this type of support. If you think about the live streaming, all the processing has to be done in a stream of data. Otherwise, you need to buffer it all on your PC before you could able to play them back. Or think about a very basic ISP function where we need to do some color space conversion and the resize of the camera data. Before it's sent to ID process, you need DP that runs a neutral network. We need to before we send it to ID and unit that runs on a neural variable requiring so before we send it to the ID processing of the unit DP that's running on a neutral network requiring a much small resolution video input. Regular OpenCV function implemented, the CPU only are gonna be operating entirely out of the memory against the frame data that are stored in here. So it cannot support streaming interface like we can with our hardware accelerators, and really vanish outcomes in that most of the OpenCV functions operate in per pixel of computation method. So we can support this 1 pixel at one time as a continuous processing of the incoming pixel data. The port on these functions support the AXS stream protocol and leverage the MAT container object. Yes, which is an image container class, the MAT container object. You can think of an MAT as being short for matrix. A 2x2 representation or image data that gives explicitly that gives copied from OpenCV-MET implemented to the Xilinx accelerated CV-MET library. And I can store physically in continuous memory space to achieve the best performance possible. Next, we have a window buffer that I used for the functions that processing pixels using neighboring data from multiple lines of the image data, which such as the 2D filter implementation. These line buffers are implemented using the BRAMs or UltraRAMs on the FPGAs. So as illustration of the streaming video processing and its advantage, let's take a look at the design where OpenCV functions are used for color space conversion and the image resize to pre-process our HD resolution video camera input before it passes to GPU. Before it passes to GPU, which is running on face detection, the neural network influence engine, and you can take a result, take the result output and do a little post processing to draw a bounding box around the face, and we will see our display. We get a performance of 18 frames per second. It gets output to the monitor. Now we take exact same processing application and accept using Vitis Vision Library is the replace the OpenCV function call here, and implement this programmable logic using streaming interface to form a pipeline. It doesn't have to buffer up the entire frame data like we would with the Vitis, with OpenCV implementation on the CPU. The result here is that you see is just by replacing the pre-processing pipeline with Vitis hardware acceleration, we're able to get even better overall output. Yes, here we got the output, and the frame per second is increased to 60. Now we can support this HD video stream of the cameras made a frame rate of 60 frames per second without any drop framework. Another major difference for us over CPU-based OpenCV is parallel, or the ability to compute multiple operations. And for video, it usually means a picture in parallel. And developers might want to do this because they have increasing need to reduce their latency. And the parallelism can bring another dimension to achieve those results. I may notice that many of these things come in groups of here, and the one is no different. Your first method for achieving more parallelism would be increase the number of pixels that are perceived at the same time. And this will be seen at that MPC turn comes here again, the number of pixels per clock. And the most Vitis Vision Library functions are gonna support this capability through the template parameters. There is always engineering trade-off. It is involved. And so here the request for Vitis is to implement multiple PL resources in parallel with the goal of decreasing our overall latency. And from the sample results that you see down here for this, the demosic kernel, you see it is cheap. The almost linear decrease in latency per increase in the MPC value over here. And the second parallelism mechanism that we can deploy is that the kernel level. We can implement multiple instances of kernel to run all running parallel, since most kernel will support its capability. And there is also a technique called batching, or multiple images or frames are fed into a pool of kernel's instance to process each of the frame continuously. Now, finally, the third mechanism for parallelism is that is at function level, and it is often referred to as pipeline. In this case, we have multiple different kernels that get stitched together with output of one time to the input of the next, and using streaming interface to form a processing pipeline. Since the streaming interface are used between kernels, most of the kernels support pipeline. And in the meantime, you can see some of the example and implementation here in the level 3 folders of the Vitis Vision library on the GitHub. And so let's cover some of the key highlights for the Vitis Vision library. They are actually used in over 90 program logic applications that are ranging from image signal processing, simultaneous localization, and mapping for navigation applications. We see this a lot in robotics, perception stacks, and there is also many machine learning inference applications that use this as a pre-processing engine as well. And so there are now more than 15 AI engine accelerators, which is pretty exciting because you can do the pre-processing pipeline on AI engines that are very close to the deep implementation on our Versal architecture. Our engineer team actually performs over 600 rigorous tests on the configuration for those accelerators during their optimized testing for each release. And finally, data movers and converters that can be used for both PL implementation as well as the AI engine-based accelerators. Finally, there is a lot of flexibility using Vitis Vision library with different tools and frameworks, and very thin how XRT and OpenCL can fit into a vision application using plugins and the drivers to access beyond the level 3 functions. We also tie in strong cohesion into the VVAS and the GStream plugin examples for video application. The ROS2 hardware accelerated node is something that we are actually working on with a pre-procession application for our recently released KR260 robot kit. As it is about mentioned, if you see something that you feel it is an important framework trend, please contact us. Finally, it's about the design methodology. I will take a very quick look at the design flow of the PL build flow and the AI engine build flow. Here shows the design flow for targeting programmable logic using Vitis Vision library, and we will see how Vitis can help developers make key decisions about the application. Help them determine factors like what software functions should be mapped to processing kernels, how much parallelism is going to be needed, how much should be targeted into programmable logic. I'm also look forward into some of the resources available for implementing vision solutions using Vitis design methodology. I do have a link here for you you can refer to. From a high-level point of view, the overall development process is presented as by this stack shown here on the right. For the hardware, the software developer can leverage the Vitis tool to utilize C and C++ language to prepare the accelerator code to fit within their accelerated applications. Once they either define their own libraries or some of the Vitis Vision libraries, they can create this HLS kernel wrapper to go around the accelerator course, makefile-driven compilation down here, calls the HLS compiler here to generate the underlying implementation, which outputs of the hardware bit stream, Excel bin, and the XRT can be used either to evaluate this implementation in simulation using hardware emulation or directly execute on our target hardware by deploying the programmable logic of the target device. And the next section is about the AIE application development flow. AIEs are AI engines, and a lot of questions on how did your development work for them work. This design flow helps to target Vitis, Versal adaptive computer accelerations platform. And in order to do this, we need to create this adaptive design flow, ADF graph. We need to set up virtual platforms, and then we need to write this corresponding host code from a high-level point of view. The overall AIE build flow is represented by the stack shown here. And so the hardware and the software developers take Vitis tool again to use C and C++ language for creating accelerator code and fit this within their application. And they can either define their own libraries over here or leverage our Vitis accelerated library over here. And they create this data flow graph in the AI using the AI engine compiler, and can figure the platform ports of these accelerator kernels and start connecting them together. And Makefile-driven compilation, because the AI engine compiler underneath hood is in order to generate the underlying implementation. And the XRT can then be used to either evaluate the implementation in simulation or using AIE or x86 simulation. Or we can use the hardware emulation or directly execute on hardware by deploying the AI engine of our target Versal device. So I have a handy link here for you that you probably wanted to bookmark so that you can have a direct access to the AI engine design methodology and the AI engine methodology here. Okay, that's all for today's sharing. Do you have any questions? Over the Vitis Vision Library?
Yes, actually, either question on the Vitis libraries or the Vitis platform is fine. And I have to say it's unfortunately because we can't do it in person, so we can arrange the hands-on for you. So it's a pity. Okay, so if there's no further questions, I think we may end today's sessions. So let me leave both one and my email address or here, and if you have any further questions or other questions during the run, you can go ahead and contact us. Well, you may also leave your emails in the chat window. Okay.
Okay.
Thank you, Joshua and Wen, for the wonderful session. Yeah, I think we don't have any further question. If anyone
Yes.
from the audience want to contact you, they can either in the gather space or through your email. Yeah.
Okay, thank you. Thank you. Both Wen and I have leave the emails here. So if you have any further questions when you look at the tutorials or libraries, please feel free to send us emails. Okay. Okay, so that's all for today's tutorial session. Thank you again. Have a nice day.
Bye.
Bye.